Hi, welcome back to part 2 of the lecture on symmetry-protected topological phases and topological indices in quantum spin chains. This is Hal Tasaki. So in this part 2, I'm going to discuss the index that characterizes SPT phases, and the latest, the most general one is called the Ogata index. Okay, and this part 2 is going to be more advanced than part 1, but I hope it's understandable. So let's get started. So I start from mathematics about index for projective representation. So I assume that you know what a group is. So let G be a finite group, and this will describe the symmetry of our quantum mechanical model. And I also assume that you know what a representation of a group is. A representation is a collection of unitary operators, UG indexed by G, the group element, that satisfies these relations. Of course, GH denotes the group multiplication. And in this part too, I use mathematician's notation. So actually, these are operators, but I drop these hat. Okay, so projective representation is something very similar to representation. It's again a collection of unitary operators, but they satisfy this relation. So the difference is here, this phi. What is this phi? Phi is a phase factor. So it's an arbitrary phase factor, or more precisely, it's a complex number with absolute value 1. And this phi is basically arbitrary, but of course, these U operators must satisfy associativity. So if you combine this associativity and this rule, you find that phi must satisfy this non-trivial relation for any FGH. And for some reason, this relation is known as cocycle condition, and phi is called A2 cocycle, but you don't have to worry about this terminology. And so by Z2, we denote the set of all two cocycles. Okay, here's a remark for experts. We can also treat projective representation with anti-unitary operators like time reversal operator, but we just stick onto unitary in this talk. Okay, so suppose that we are given projective representation described by this set of unitary operators. Okay, and then I pick an arbitrary phase factor psi and define U prime this way. And of course, this U prime satisfies this relation. So it also gives projective representation with this new phase factor. But since UG and UG prime are related by this trivial relation, we want to regard them as giving equivalent projective representations. Okay. And so this motivates us to define this equivalence relation. We say that phi and phi prime, they are two cocycles. They are equivalent with each other if and only if there exists some phase factor psi and phi prime and phi are related by this relation. Okay, so this is an equivalence relation. Then you can consider the set of equivalence classes with respect to this relation, or the quotient set. And this quotient set is denoted as H2. And this naturally becomes an abelian group because we start from U1. And this is called the second group cohomology. Again, you don't have to worry about this fancy name. Okay, so by definition, an element of H2, which I call index, IND, characterizes an equivalence class of the projective representations of G. Okay. One very important property of these indices is that we can add them. So suppose that we have two projective representation of a single group G, and I denote them by UG and UG1 and UG2, and they have index 1 and index 2. And then you consider the tensor product of these two. And of course, by this also gives a projective representation with this new phase factor phi. And I want to describe H2 as an additive group. So this means that the index for the new projective representation is simply the sum of two indices. Okay. And here comes an important example, Z2 cross Z2. Z2 cross Z2 is a very simple abelian group that has 4 elements like this. And this is a bad notation, but this is a useful notation. E is, of course, the identity. And X, for example, denotes the pi rotation about the X-axis. So Y and Z also denote the pi rotations. And then they satisfy this group multiplication rule. I think you can understand them. And if you compute the second group cohomology of this group, you find that it's C2, 0, 1. So the index can be 0 or 1. Very important example is actually you don't have to understand the abstract theory, but you need to understand this particular example to understand the rest of my lecture. So the important example is the projective representation of Z2 cross Z2 given by a single quantum mechanical spin. So this is our spin operator, and S is the spin quantum number. And then define these unitary operators. So this is just identity, and this is the pi rotation operator in the spin space. And then you easily find that this U satisfies this relation. And of course, this recovers this Z2 cross Z2 rule. Furthermore, if the spin quantum number S is an integer, then we find that this UG squares to be identity and they commute with each other. And in this case, these U's perfectly recovers this group multiplication rule. This means that this U gives a genuine representation, a usual representation, or a trivial projective representation. But if the spin quantum number S is a half-order integer, then for GH x equal xyz, you find that UG squares to be minus the identity, and more importantly, they anti-commute with each other. So in this case, we have extra phase factor. So this gives us a non-trivial projective representation. So here's the very important summary. Okay, if your spin, local spin, is an integer, then you have a trivial projective representation and the index is 0. If the spin is a half-order integer, then we have a non-trivial projective representation of Z2 cross Z2, and we have non-trivial index 1. Okay, so this is important. Okay, so let me move on to the next task of defining similar index for a unique gap ground state of infinite spin chain. So for this purpose, I want to consider spin systems defined on infinite chains. And here's the general formulation in terms of Cstar algebra. So this is a bit mathematical, but don't worry. I just briefly discussed the setting. So here's the chain, infinite chain, which is Z. And I assume that for each site in this infinite chain, we have a Hilbert space, Hj, whose dimension is finite. And by a local operator, I mean operator that acts non-trivially on this finite dimensional Hilbert space corresponding to finite subset of the chain. So by local, I don't mean that it acts on a single site. It may act on several sites, but only on finite number of sites. Then the basic object is called the Cstar algebra and denoted like this. It's called R or A. And it's basically the set of all local operators in this sense. Okay. But I take completion with respect to the operator norm. And let G be a symmetry group that is a finite group. And I assume that for each local Hilbert space, we have this set of unitary operators that gives a projective representation of the group G. And I denote by INDJ. I call this the spin index, the index at this site J. Okay, so this is something sort of easy. You know when you define your unitary operator, UG. And since we have this unitary, of course, we can think about transforming a local operator. So let A be any local operator. Then we can transform this A like this simply by sandwiching A by U and U dot R. Actually, this is mathematician's notation. So this is usually U dot R. Okay, and you easily find that this Xi, mathematician called this star automorphism. This Xi satisfies this relation, so it gives a kind of representation of the group. Okay, so we consider a G invariant short-ranged Hamiltonian, which describes our spin system. And this is a formal definition. This is an infinite sum, so it doesn't make sense. But the essential fundamental object is Hj, the local Hamiltonian. The local Hamiltonian is a self-adjoint operator that acts on a finite portion of the chain, including the site J. Okay, and I assume that it is invariant under G, the action of G. Okay, actually, more precise, the action of psi G. Okay, and then the basic assumption is that the ground state omega of H is unique and accompanied by a non-zero energy gap. H has a unique gap ground state omega. But we have to be careful about the notion of unique gap ground state in this infinite chain. And here's the abstract definition in the language of Cstar algebra. But you can imagine omega as this limit heuristically. So here is a local operator. So you just take expectation value with respect to this ground state in a finite chain with length L, and then you take a certain limit, L infinite volume limit. So this omega A gives the ground state expectation value of any local operator A. Okay, so in more general, in general, in this Cstar language, a state in general is a linear function omega from R to C such that these properties are satisfied. So this omega gives the expectation value of a local operator A in a state you're considering. And okay, so here's the definition of a ground state. So a state in this sense is said to be a ground state if and only if this inequality here is valid for any local operator A. And this looks like a mysterious relation, but it's not. So suppose, okay, consider a finite volume, usual quantum mechanics, and suppose that phi is an energy eigenstate with an eigenvalue E. And then, and as I said, this omega denotes the expectation value. So this relation, this mysterious relation reads like this in this finite volume language. And now, if you simply expand this and use the fact that phi is an energy eigenstate, you easily see that this inequality is rewritten in this way. But this has clear meaning. What is this? Well, this is the energy expectation value in the state A phi. So this means that you initially had the state phi with energy E, and then you applied, you acted on phi by this operator A to get a new state, A phi. And so the left-hand side is simply the energy expectation value in this new state A phi. So this is the variational characterization of a ground state. So this means if this is valid for any A, that this means that you cannot lower the energy of phi by hitting phi with A. So that is the usual definition of ground state. So now you are convinced, I hope, that this is a very straightforward generalization of this idea to infinite state. So you start from omega, that is the infinite volume ground, that is a infinite volume ground state, and by hitting this state by A, this says you cannot lower the energy anymore. Okay, and the third one is a definition of a unique gap ground state. So a unique ground state omega is said to be accompanied by a non-zero energy gap if there exists non-zero constant gamma, positive constant gamma, and this inequality is valid for any A such that this is valid. And I'm not going to demonstrate this again, but if you again go to finite volume language and do the similar consideration, I think you will be convinced that this is again a natural generalization of what we think about unique gap ground state. Okay, so these are the formulations, but you don't have to be too careful. So please just have this in mind. So omega is the infinite volume ground state, and it's basically gives the expectation value of a local operator. Of course, very important examples are Z2 cross Z2 invariant chains. So we have this infinite chain, and on each side we have spin operators, and the projective representation of Z2 cross Z2 is given this way. as I discussed before. And here's the spin index. It's very simple. The spin index is 0 if the spin at J is an integer. The spin index is 1 if the spin at J is a half odd integer. Okay. And these are the pi rotations of the operators. And of course, this is pi rotation about X. And so Sx does not change, then Sy and Sg change their signs. And here are two very important examples of Z2 cross Z2 invariant models, Hamiltonians with a unique gap ground state for spin 1 chain, AKLT chain, and this trivial chain. Okay, so these are the examples I discussed in part 1. Good. Okay, so now I will move to the task of defining an index for a G invariant unique gap ground state omega defined on infinite chain. So here's omega. So to investigate this state, I will make a transformation corresponding to G. Okay, what happens? Well, nothing, because I said omega is G invariant. So nothing can happen. But this is not the end of the story. We can think about picking an arbitrary site J and making a fictitious cut at site J. And by concentrating on the state restricted onto this half infinite portion of the chain, and then we might see a non-trivial transformation property, then we might be able to define a new non-trivial index that I denote with this I and the uppercase I and the index J, because it may depend, it can depend on J because we made a fictitious cut at J. Okay, so we may be able to define such an index. Okay, so before defining the index, before discussing the definition of index, I want to discuss examples. So these are wishful examples. So consider very simple Z2 cross Z2 invariant spin 1/2 chain with this Hamiltonian. This looks like the Heisenberg antiferromagnetic Hamiltonian, but no, this is not. Be careful, because the sum is over 2J and 2J plus 1. So this means that there is an interaction between site 0 and 1 and between site 2 and 3, but no interaction between site 1 and 2. So this is a very, very, very simple problem. And you can easily find the unique gap ground state, which is simply this. This is essentially two spin problem. So the ground state of the whole chain is simply the tensor product of this spin singlet formed by 2J and 2J plus 1. And I note that I think you know that spin singlet is rotationally invariant. That means this is, of course, Z2 cross Z2 invariant. Now, so you have this. Oh, okay. By the way, so this, again, this two dots connect. These dots are spin 1/2, and this denotes a spin singlet. Okay. Now, I make a fictitious cut here and examine the transformation property of this half infinite portion of the chain. Okay. But here in this half infinite portion of the chain, you only have a bunch of spin singlets, which are innocent, which are Z2 cross Z2 invariant. So if you look at the transformation property in this half infinite portion, you don't get anything. You see nothing. So in this case, index should be 0. But you can also think about making a fictitious cut here between 0 and 1. And then in this case, you again have a bunch of innocent spin singlets, but you have a single spin 1/2 at the edge. So if you examine the transformation property of the states, the state restricted on this half infinite portion of the chain, you will see the transformation property of this single spin 1/2. And in this case, then you should get an index which is 1. This is int 2 because I cut it here. This is int 1 because I made a cut here. Okay, good. So this is a basic example. Here are more non-trivial examples for spin 1 chain. And then I start from this trivial Hamiltonian. Then the unique gap ground state is given by this. And of course, 0 alone is Z2 cross Z2 invariant. So if you make a fictitious cut here, this is translation invariant. You can cut anywhere and examine the transformation property. You don't see anything. So you should get 0. And on the other hand, this is the AKLT model with the exact VVS ground state. So here's the VVS state. And as you remember, these dots represent spin 1/2, and this is symmetrization, which makes two spin 1/2s into spin 1. And in this case, if you make a fictitious cut here and examine the transformation property of this half infinite portion of the chain, again, you have bunch of innocent spin singlets, but you see an effective spin 1/2 at the edge. And actually, this spin 1/2 is not strictly localized at the edge. It's sort of exponentially localized because of the symmetrization. But anyway, it's sort of localized. So when you examine the transformation property in this half infinite portion of the chain, you should observe the transformation property of a single spin 1/2 again. So in this case, the index, the corresponding index, uppercase index, should be 1. Should be. We haven't defined the index yet, but they should be 1. Should be 1 and 0. So in this case, this index can distinguish between these two states. Very good. So how should we define such an index for unique gapped ground state? So one natural idea is that to take a large but finite system and very, very large system and examine transformation property of this part. This is actually half of this long chain. But this idea does not work at all. In this case, actually index is trivial. If you want to define index in this way, then actually the only way is to simply sum these spin indices. And these are, of course, something you already know. And so this does not reflect the property of the ground state at all. So this is pretty bad. In particular, if we consider these two unique gapped ground states, then index defined in this way is 0 for both the states. So this index cannot distinguish between these two states. Okay, it's a bad news. Good news is that if we work on matrix product states, more precisely something called injective matrix product states, we can define meaningful index. That is a work, very famous work of Paul Montano, Bauk, and Oshikawa back in 2010. Okay, so I already discussed what matrix product states are in part 1. So I think you already know it. It was invented by these people. And so suppose that we have a G invariant injective matrix product states. And then I will apply transformation corresponding to some group element G to this, this state. And I will discuss an example in the next slide, but then you can show that this, the effect of this transformation can be sort of absorbed into a transformation of these matrices defining the matrix product state. And so, yes, and you will find that if you try to transform this state, this induces the transformation of matrices like this. So M changes into M tilde. And this theta is just a constant. So the essential object is this UG star. So UG is a matrix, which depends only on G and which does not depend on sigma. So anyway, matrix transforms in this way. So this is a graphical representation of this transformation. So this is the original matrix product state. And then you make this transformation, M to UMU on each side. So they become UMU star, and so on. But now I would say that this leaves the state invariant because here, this is just a product. So if you multiply this and this, you see that U star and U cancel, U star and U cancel. So actually this is the same as MMMM. So this represents the invariance of the state. But if you make a fictitious cut here, and if you concentrate on this half infinite portion of the chain, then of course, these guys can cancel with each other, but this poor U remains alone and cannot, and it's sort of visible. So if you look at this transformation property of this half infinite portion of the chain, you start observing the transformation property described by this U. And now very interesting fact is that this UG gives us a projective representation G of G. And from this projective representation, we get the desired index, IND. And this desired index does what we want. For example, if you define the index that way, actually, so Pullman, Nobelko, and Oshikawa did that. They found that the index is 0 for this trivial state, and index is 1 for the BBS state. Okay, so that, as I said, this is a work by Pullman, Nobelko, and Oshikawa in 2010, but there is a very closely related work in 2008. And also in math community, they were looking at something very similar, much earlier. But anyway, so in the context of SPT, this Pullman, Nobelko, Oshikawa paper is very, very important. And they computed these indices. Okay, so let me just discuss one example of how to compute this Pullman, Nobelko, Oshikawa index. So this is, of course, explained in their paper, but it's very, very hard to read. So if you are interested in the details of the calculation, please look at my book. So I have no contribution at all on this subject, but you can read my book. Okay, so as an example, I take the BBS state, which is the exact ground state of the AKLT, Hamiltonian, and which is C2 cross C2 invariant. And this is a graphic representation of the BBS state, and this is the matrix product representation of the BBS state. These are matrices. Now, I consider one of D2 cross D2 transformation that is a pi rotation about the z-axis. So it's described by this unitary operator, and you easily find that if you apply this to the basis state, you only get this phase factor. Okay, if this is 0, nothing, because okay, you easily find it. Okay, so this is the pi rotation operator, global pi rotation operator. So I apply this rotation operator to BBS state. Good. And of course, this applies to not to here. This is just a coefficient. So this unitary operator applies to these basis states. So by using this rule, you find that here you get this extra phase factor. Now, what you want to do is, as I said, I want to absorb this phase factor into matrix product. So I define new M tilde by this, and then this -1 factor is absorbed into this matrix. Okay, so this is a definition of M tilde. And these are just trivial, very, very trivial observation. One non-trivial observation is that you can rewrite this by using a sigma independent matrix UZ and this way. Okay, you know, so this is simple, but this prefactor depends on sigma. But look here, UZ does not depend on sigma. So, and I say that for any sigma, 0 plus minus, this can be written in this way using this UZ. So this is the important matrix. And so similarly, we can consider pi rotations about x-axis, y-axis, and obtain corresponding matrices. Oh, okay. So to show this, of course, you need to use this specific form of matrices. Okay, this is not a general relation. This is something you find by examining this particular matrices. Okay, and so by examination and computation, you find that these three matrices will do, and you will easily find that this UX, UY, UZ gives us a non-trivial projective representation of Z2 cross Z2, which has index 1, non-trivial index 1. By the way, probably you have noticed that these operators are precisely the pi rotation operators for spin 1/2. Look, so very interestingly, we are treating a state of a spin 1 chain, but here this U that describes the transformation property of the edge is precisely the pi rotations for spin 1/2. But it's consistent with our picture that there appears edge degrees of freedom, which had spin 1/2. Okay, so we have seen that we have desired index, but that it's only for injective matrix product states, injective MPS. And injective MPS is a very large class of states, but still, they are very, very special and limited, and you have to have translation invariance and everything. So we need much more general definition of index to discuss SPT phases in general. Okay, now I will discuss the Ogata index. This is the desired index, general index. So in 2018, based on earlier works by many mathematicians, including that of Takumatsui, Yoshiko Ogata gave a definition of index, her index, IND, that takes value in the second group homology for any G invariant unique gap ground state. More generally, for any pure split state. Don't worry about this terminology. So for any G invariant unique gap ground state. And this does what we want. Okay, so it characterizes the transformation property of this half infinite portion chain and so on. And this is not an easy thing. And for the definition, you need operator algebraic Cstar algebra formulation of spin chains. And also you have to treat something rather difficult, like the representation on the type 1 factor and so on. So it looks like a magic for most of us. But if you're interested actually I decided to make one more video. So there will be an appendix for this lecture. So this will be 3-part lecture actually. And there I will briefly discuss how you define this index. Anyway, so we have it. So let's look at basic properties of this Ogata index. So omega is again G invariant unique gap ground state, and J denotes an arbitrary site. Then we have for each site, and of course for each omega, we have well-defined index that takes value in the second group cohomology. And first of all, this is very important non-trivial theorem that Yoshiko Ogata proved. And her index is identical to the index of Pullman, Turner, Belk, and Oshikawa if we restrict ourselves to injective matrix product states. This is very important. So this is a strict generalization of Pullman, Turner, Belk, Oshikawa index. And this is a non-trivial theorem. And this is a very difficult theorem proved by Ogata. This index is invariant under smooth modification of G invariant models with a unique gapped ground state. So this is in a sense topological index. Further properties, this is a property called additivity. So look, so this INDJ describes the transformation property of this half infinite portion of the chain. INDJ plus 1, index J plus 1 denotes, describes the transformation property of this half infinite portion of the chain. And here, lowercase IND describes the transformation property of a single spin here. So this is a spin index. And then please keep in your mind that this lowercase IND is something very simple. For example, if the case of in the case of Z2 cross Z2 invariant spin chains, then this lowercase IND is something you already know. Your spin, if your local spin is an integer, then it's 0. If it is a half-order integer, it's 1. Okay, it's something you already know. But anyway, both of them, all of them describes transformation property of some quantum mechanical object. So it's very natural that this additivity is valid, right? Because this can be divided into this and this. So this should be the sum of this and this. And this is very much expected, but it is true. So it was proved by Ogata, and it's actually the proof is written in our joint paper. But of course it was proved by Ogata. And this is another additivity. We were only looking at the transformation property of the right infinite portion of the chain, but of course you can make a cut here and examine the transformation property of the left half infinite portion of the chain. And if you add and define this left index, and then if you add this left index and the right index, the sum should be 0. Why? Because if you add them, then you recover the whole chain. And as I said, the whole chain is simply invariant, so you shouldn't get anything. So this is 0. Again, this is proved by Ogata. Okay, another property is the transformation about inversion, but this is rather simple. So suppose that we have a unique gap ground state omega, and I make this inversion transformation. It's just a flip. around 0. 0 stays the same. 1 goes to -1, -2 goes to 2, and so just a flip. And by this flip, you get a new spin chain and a new ground state. But just that's trivial, but you get a new ground state omega bar. Then I say that the index in this new state omega bar, new ground state omega bar, is related to the index of the original state by this. Well, this looks complicated, but this is just very, very easy. So this is original omega, and this is a portion you're looking at. You just flip everything. So this region becomes this region. So this means that this index for omega is equal to the index, left index of omega bar. And I use the additivity to get this equality. So this equals this. Okay. But you don't have to worry about this too much. This graphical representation is enough. So this is a summary of the useful properties of Ogata index. Ogata index, the definition is very difficult, but to use it is rather easy. You should only know this rule. So to make our notation simple, by lowercase ij, I denote this spin index. So this is something you already know. And by uppercase ij, I denote the Ogata index. So this is something difficult. You need von Neumann algebra and so on. And so this is Ogata index for omega restricted onto this half infinite chain. So this is omega, a ground state. G invariant ground, unique gap ground state, and these are spin indices. So you know this already, and these are non-trivial Ogata indices. Then first of all, additivity says that, for example, I2 that describes transformation property here is equal to lowercase I2 plus I3, okay? And here's the inversion. So you start from omega and just make this flip about the origin. And then first of all, local spins are simply flipped. This comes here, this comes here, this comes here, and so on. And Ogata indices are also flipped, but it's non-trivial. So if this comes here, but with minus sign, this comes here, but with minus sign, please remember this. Okay, so we will use these properties in the next part. As an application of Ogata index, so I will discuss the problem of classification of SPT phases. So this is the main problem of this lecture, I think. So this is something I already explained in part 1. So this is the definition of SPT phases. So let H0 and H1 be G invariant Hamiltonians of the same spin chain, and which have unique gap ground states omega 0 and omega 1 respectively. And then we say that the two models belong to the same SPT phase protected by the symmetry G if and only if there exists a family of G invariant Hamiltonians HS with the property that HS has a unique gap ground state for each S, and this omega S depends smoothly on S in certain mathematical sense. Okay. Now, this is a definition, and here comes Ogata, and now we have Ogata index J omega, which is well defined. And here's the essential theorem by Ogata. This is basically a consequence of topological nature of Ogata index. And we now know that if the index that say the origin of the two ground states are different, then the two models belong to different SPT phases protected by the symmetry G. Or more, in other words, you can never smoothly connect H0 and H1 through G invariant models with a unique gap ground state. Okay, so this is a fundamental theorem. And here I use the Ogata index at the origin, but you don't have to use origin because anyway, we know all these local spin indices. So if you know the Ogata index at the origin, then of course by using this additivity, you know Ogata index for all other sites. Okay, so this can be an arbitrary site. Okay, let's look at an example. So this is the example that we have been looking at repeatedly. So consider a spin 1 chain, and first of all, take this trivial Hamiltonian. And then this has a unique gapped ground state, trivial ground state, which is simply the tensor product of zeros. And in this case, one can easily compute Ogata index. Actually, it's the same as Pullman, Turner, Belk, and Oshikawa index. This can be written as an MPS. And I didn't demonstrate, but this is very easy. And you simply get 0 index for everywhere. Of course, it's trivial. And of course, the second example is the AKLT model with this VBS state. And in this case, again, Pullman, Turner, Belk, and Oshikawa computed the index. I explained the calculation, and you get 1. And now you pick a bond and compare them. And of course, they are different. So you can conclude that the two models can never be smoothly connected through Z2 cross T2 invariant models with a unique gap ground state. In other words, they belong to distinct SPT phases protected by Z2 cross C2 symmetry. So this is a very important consequence of Ogata's index theorem. Okay. Let me discuss a less interesting example. So I take Z2 cross Z2 invariant spin 1/2 chain, again dimerized chain. So this looks like the Heisenberg antiferromagnet, no, but this is just this 2J plus 1 thing. So in this case, the ground state is simply the tensor product of spin singlets. Okay, here's is the same basically the same Hamiltonian, but everything is shifted by unit lattice spacing. Okay, now 2J minus 1 and 2J interact. So the ground state is again trivial, and this is simply the shift. So this denotes spin singlets. So this is the ground. If this is the ground state of this H0, then the ground state of H1 looks like this. Everything is shifted by 1. Now in this case, again, you can easily compute Ogata index, Pullman, Turner, Belk, Oshikawa index, and you find that it's 0, 1, 0. Of course, here it's just about, I told you the heuristic argument. So here it's everything is invariant. But if you do this, you see extra spin 1/2, so you get 1. And so you get this Ogata index 0, 1, 0, 1, 0, 1. As for this one, you get 0, 1, 0, 1, 0, 1. And as I said, these are the same thing, only shifted by this unit lattice spacing. But if you pick bond and compare the Ogata indices at the same bond, and then they are different. They are different. So you conclude that if you try to connect these two states through Z2 cross Z2 invariant spin chains, you can break translation invariant, you can do whatever except for breaking Z2 cross Z2 invariance. And if you try to do that, you can never connect them smoothly. So in other words, the two models, the two ground states belong to distinct SPT phases protected by Z2 cross Z2 symmetry. This is a bit weird. They are the same thing, but this from the definition, we get this conclusion. Okay. Well, Ogata's result applies to much more general case. So this is a general classification given by Ogata. So for any G invariant quantum spin chains, you don't need translation invariance. SPT phases protected by the symmetry G are classified by a single index, Ogata index, say at the origin, that takes value in the second group cohomology. So this is a very artificial example, but consider a Z2 cross Z2 invariant spin chain with site-dependent spins. So this is just arbitrary, but suppose that spin on each site is very different. And it's kind of random like this. And in this case, local spin index is given like this. I mean, this is integer, it's 0. This is half of the integer, it's 1, and so on. And now you ask, what kind of Ogata index is possible? Because we always have to have this additivity. There are two choices. So Ogata index, the configuration of Ogata indices in this weird model can be like this or this. These are the only two choices that is consistent with this additivity. So we conclude that in this case, there are at least two phases, two SPT phases protected by Z2 cross Z2 symmetry in this model. And in each phase, the Ogata index is given like this. So I repeat, so this is the general classification by Ogata which was given in 2018. And I would say that this is a strict extension of the known classifications. The known classification number one is something I already discussed, that by Pullman, Turner, Belk, and Noshikawa. And this works for injective matrix product states. So, this is basic, and you can compute many indices by using their formulation. But anyway, it's limited to matrix product states. In particular, you need translation invariance, definitely needed. And the other is a classification by Cheng-Gu Wen given in 2011. And this is based on the consideration of fixed points of some RG renormalization group transformation. So this means to discuss RG fixed points, you need some uniformity. So of course, Ogata doesn't assume any uniformity or any translation invariance. So in this sense, Ogata's classification is a strict extension of these known classification given in physics literature. And here's the final remark. This is often the case for index theorems. It is possible that different phases happen to have the same index. So if you have two models and their indices are different, then you are sure that they belong to different phases. But it may happen that two models belong to different phases in the sense that you have to go through singular point to connect them, but still these two models happen to have the same index. Okay, so anyway, this is a very important application to the classification problem of SPT. Let me finally discuss the notion of full SPT order, full symmetry protected topological order that naturally arises if we think about the Ogata index. So I start from the definition. A G invariant unique gap ground state omega is said to have full SPT order if and only if the Ogata index is non-zero for any J. And I think you will understand the motivation for this definition by recalling these two examples. So we have seen two examples of distinct SPT phases or SPT phase transition protected by Z2 cross Z2. And one is this spin 1 chain, which is related to this old problem of Haldane gap. Okay, this is a non-trivial state, the ground state of AKLT state, which has Haldane, which shows Haldane phenomena and which has Haldane gap. Here's the trivial one. And there was a phase transition. And here is the dimerized spin 1/2 chain. And these are the same thing, only shifted by unit lattice spacing, but we have seen that they belong to distinct SPT phases and there is a phase transition. But we sort of feel that this example of spin 1 is more interesting, less trivial, and this spin 1/2 case is less interesting. But now this definition tells one interpretation, gives one interpretation, because in the spin 1 case, this is indeed a transition between a state with full SPT order, you have the index non-zero everywhere, and a state without full SPT order. On the other hand, in this spin 1/2 dimerized case, neither state have full SPT order. So this is a phase transition between a state without full SPT order and another state without full SPT order. So this is one motivation. The other motivation comes from the relation between entanglement and SPT order. So let Sj omega be the entanglement entropy between, which is defined when we make a cut between J and J minus 1. Okay. Also, you have to be, the precise definition can be found, for example, in Ogata's paper, we are in infinite chain, but you can define the entanglement entropy properly. And then Ogata proves back in her first paper that if omega has full SPT order, then for any J, this entanglement entropy is lower bounded by log 2. So wherever you make a cut, you see entanglement. You must have entanglement because of symmetry. So this kind of entanglement enforced by symmetry is one of the essential properties of SPT phases. Okay, so this illustration shows that wherever you cut, you see something. Okay. Now here's a simple but rather interesting necessary condition for full SPT order. So here's the theorem. It's very easy, but it's a theorem. Suppose that the second group cohomology is 0, 1. So this is the case when we have Z2 cross Z2 symmetry or time reversal symmetry. Then full SPT order is possible only for a spin chain with spin index 0 for all sides. Okay, this is the theorem. How do you prove it? The proof is very, very easy. So we assume that this ground state has full SPT order. Now, since the second group homology is 0 or 1, the only possibility is that you have our Ogata indices, so 1 everywhere. So yes, okay. So from the fact that this has a full SPT order, we know that Ogata indices are 1 everywhere. But now, I think you know the proof now. Ogata indices must satisfy this relation. This equal additivity. This is 1, this is 1, then this lowercase ind should be 0. Very easy computation. So you can, this is rigorous. Now you proved that spin index must be 0 everywhere. And this is consistent with the fact that we find Haldane fades protected by on-site symmetry only for integer spins. Okay. We knew that we don't have any Haldane fades for half-order integer spins when it is protected by on-site symmetry, but this proves the fact as a general theorem. Here's a remark. We didn't assume any translation invariant here, but if you further assume translation invariance, then we can treat any symmetry and we get the same conclusion. You can say that this is a kind of Lipschutz-Matisse type theorem, if you know what this is. If you apply this notion to half-infinite chains, you make some easy but non-trivial observation. So consider a spin system not on the infinite chain, but on the half-infinite chain. It has an edge, and the other side is infinite. And you consider any G invariant unique gapped ground state, omega, defined on this half-infinite chain. In this case, I claim that Ogata index here at the origin is 0, because well, in this case this Ogata index represents a transformation property of this half-infinite chain, but this is the whole system, and the whole ground state is G invariant, so this must be 0. And of course, in this case too, Ogata indices satisfy this additivity property. This means that you can simply solve this to obtain Ogata indices completely in this case. Okay, this looks surprising, but of course this assumption that we have a unique gap ground state is very strong. So if you assume this, then we automatically know all Ogata indices. Let's look at some examples. So again, I consider the standard case where H2 is 0, 1, like the standard Z2 cross Z2 invariant case. So consider usual integer spin chain. Integer spin chain means all the spins are integer, like spin 1, and all the local spin indices are 0. And then, of course, in this case, we see that all the Ogata indices are 0. Okay. Of course, we have this assumption that there is a unique gap ground state, but in this case, we don't have any SPT. On the other hand, this looks a bit artificial, but consider a chain in which the spin at the origin has index 1, and all other spins have index 0. So this is a spin. This is a chain where you have spin half-order integer spin, like spin 1/2 at this origin, and all the other spins are integer. Like so, you have spin 1/2 here, spin 1, 1, 1, 1, 1, 1 here. So in this case, if you solve this relation, you find that Ogata index is 1 for all bonds. So this means that, oops, oh, here's a typo. This should be, I'm sorry, this should be J from 1 to 3. Ogata index 0 is 0, I'm sorry. So this starts from J equal 1, okay. But anyway, J equal 0 doesn't count. So this J equal Ogata index at 1 looks at the transformation property here, or the entanglement between here and here. So all the meaning for Ogata index is for J, which is larger or equal to 1. Okay. So we have full SPT order. And because I stress that this in this discussion, the assumption that we have unique gap ground state is very strong. But anyway, if you assume this, you see only by looking at local spins that the ground state, unique gap ground state must have full SPT order. Of course, this is consistent with this picture of edge spins. Okay, so here is less trivial discussion, and this goes back to something called SPDLM Theorem by these authors, and we also learned a lot from Haruki Watanabe. And okay, so let me start from the simplest example. So suppose that we have a unique gap ground state which is invariant under this Z3 cross Z3 symmetry, a bit larger group. And in this case, you find that this second group homology is Z3, 0, 1, 2. Unfortunately, this does not happen in usual quantum spin system, but suppose that we had such quantum spin system. And suppose that we have a spin chain with these local spin indices like this. And furthermore, assume that we have inversion invariance. Everything is invariant under the flip about the origin. And of course, we assume we have a unique gap ground state. And we still don't know what Ogata indices are, but suppose that Ogata index on this bond is I. Then by this invariance, we see that I discussed that Ogata index changes sign upon flip. So the Ogata index on this side, on this bond must be -1, minus I. But look, Ogata indices must satisfy additivity. So in this case, this I should be equal to 2 plus minus I. Well, this can be solved, very easily solved. And you find that in this case, Ogata index must be 1 here and -1 here. -1 equals 2 is -1 is the same as 2. So in this case, the ground state must have full SPT order and Ogata indices are like this. Okay. So in this case, what we did is we simply assumed the value of local spin indices and assumed this inversion invariance. Then we concluded that the unique gap ground state must have full SPT order. And here's the, as I said, there's no example in usual standard quantum spin systems. I think the simplest example is something called the SU3 AKLT state. I'm not going to explain this, but yeah, there is an example, a bit weird example. So importance of this consideration is that in this setting, in this spin system with inversion invariance, something non-trivial must happen, okay? Because it may have a non-unique ground state. That's interesting. Or it may have gapless ground state with gapless excitations. That's interesting. Otherwise, and the remaining possibility that you have a unique gap ground state, but we are guaranteed that we don't have a boring unique gap ground state. In case it has a unique gap ground state, it has full SPT order. So something interesting happens. That's very interesting. Okay, so of course this can be generalized, and generalization is almost trivial. So suppose that sigma is an element of the second group homology such that twice the sigma is non-zero. Okay, this doesn't happen for the case if this is C2, but anyway, suppose that, and then consider the spin chain where spin alternates between 2 sigma and -2 sigma, and further assume that you have inversion invariance. Then we find that Ogata indices must be sigma minus sigma minus sigma. So we have full SPT order. Here's a minor remark. You can replace this assumption to something else. Okay. Okay, so I think I have said everything that I wanted to say. So here is the summary of 2 parts, parts 1 and 2, but I think I don't have to read it. You can read it. So thank you very much for watching the long lecture, and goodbye.